Diode rectifier is a small part of a rectifier circuit, where a rectifier circuit is a device that is used to convert AC signals to DC signals. So if we have something like this, where we have some voltage, VAC, as a function of time, our first stage of conversion is likely going to be a transformer. And we're not going to get too heavily into transformer theory or anything in this class, mainly because I haven't reviewed that stuff since I was an undergrad for the most part. But let's call this N M. Hopefully you all recall that depending on the number of windings in the primary and the number of windings in the secondary, we can convert, let's call this the primary winding being the thing connected to that voltage source VAC on the left. The secondary winding is connected to the voltage drop VS of T. And so we can effectively step down some AC voltage to some smaller AC voltage with relatively low losses through the use of a transformer, right? So our transformer, the secondary windings of our transformer are going to be connected to the input terminals of a diode rectifier stage, which is what we're going to talk about a lot today. And the output of the diode rectifier stage is usually connected to the filter stage. And we're going to see that we can largely lump these two stages together. Then we would have the output of our filter stage feeding a voltage regulator, which we've already talked about. And for the most part, our voltage regulator's output should be a DC signal. So with regards to what our stages look like during this conversion process from an AC signal to a DC signal, let me make this slightly smaller. We should have something like this. So we have a large scale AC signal that's going to be transformed into a smaller version of that same AC signal. It'll have the exact same frequency, phase angle, and all that kind of good stuff. Our rectifier circuit is then going to do something like this, okay? Depending on the type of circuit, it might not be exactly like this, but effectively it's going to take all of our negative half cycles of our input signal and either throw them away or convert them to a positive half cycle. And then our filter circuit is going to take that and kind of give us some DC offset, and then what we're going to call a ripple on top of it. So it's not going to be purely DC, but it's going to be DC with some regions of exponential decay that we're going to talk about. And then finally, our voltage regulator, we observed when we were working with developing our small signal model for diodes. And if we feed a input voltage that has some reasonably large AC component to it into our voltage regulator, we saw that our voltage regulator did a very good job of keeping the output voltage effectively at a constant DC level. So we observed, I believe, that we could change our supply voltage by as much as 1 volt and only saw a few millivolts of change in our DC output, right? So we're getting a pretty good DC output by the time we hit our voltage regulator. And then we could obviously power some load, like the battery for your laptop or something like that. So these are the steps. We're going to be focusing a lot on the diode rectifier and the filter stage today, with a little bit of transformer thrown in as well. So let's start with a half wave rectifier, which is the concept that we finished off with. That looks terrible. Before the break. So for our half wave rectifiers, we actually have 2 different types of circuits. Let's call this diode D. This is our resistor R. This is our time varying input signal. This is our time varying output. And then over here on the right-hand side of the page, we'll look at our other half wave rectifier, which is nothing more than the exact same circuit, except the polarity of the diode has been swapped. So if we're using a constant voltage drop model, we should observe that for an input signal of a sinusoid, I'll try to draw this as least crappy as possible. So this blue curve is going to be our input signal. And its maximum value is what I'm going to call VPK. So peak value, okay? And that's something that's critically important, so I want to talk about it for just a moment here. When we're specifying a transformer, typically speaking, we're dealing with RMS voltages on the primary side and RMS voltages on the secondary side, right? So for instance, if we have a 10-to-1 transformer connected to a 120 volt RMS 60 hertz source, then the output on the secondary windings would be 12 volts RMS at that same frequency of 60 hertz, right? All of the math that we're going to wind up doing for these half wave and full wave rectifier circuits does not use RMS values of the voltage. It winds up using the peak value of the instantaneous voltage, which would just be the RMS voltage multiplied by a factor of square root of 2, okay? So whenever I'm mentioning this voltage, that is the instantaneous value of the voltage. It is not an RMS voltage whatsoever, okay? I want to be very, very clear about that. V peak has units of volts, not units of volts RMS. All right, so for our left-hand half wave rectifier, our output signal using the constant voltage drop diode model should look something like this. So effectively, our diode doesn't turn on until Vn is larger than VD on, at which point our output signal begins to follow the input signal, but there's always going to be that little discrepancy. For our right-hand rectifier, we see a similar thing, except that it's not going to turn on until Vn is less than negative VD on. So our transfer function for this guy should look something like this. Here's V out, here's V in, and let's call this voltage here VD on. We'll write a similar one for this guy. We would have something like this, where this slope is exactly 1. And in this case, it would look something like this, where again, this slope is exactly positive 1. And mathematically, we could write V out as a piecewise function, 0 volts for Vn less than VD on, and it is Vn minus VD on, Vn greater than or equal to VD on. And for our right-hand guy, we're going to have effectively the opposite relationship. Zero when Vn is greater than negative VD on, and it's Vn plus VD on, Vn less than or equal to negative VD on. Excuse me. So these are our two different types of half-wave rectifiers, okay? The applications for which we can use a half-wave rectifier are actually pretty limited, and it's because the output voltage goes through a pretty large swing, and then there is no output voltage for effectively half of the time. So what that means is that we are delivering roughly half of the power that's being delivered to a load that's being delivered to our secondary windings. For the overwhelming majority of applications, that's not okay. But there is one pretty simple application that does use this as a very simple example of pulsed power, okay? So we're going to talk about a lamp. So let's say that I have the following circuit. I have some AC voltage. Then I have a switch. I'm going to have a path up here. And a path down here. And then I have a simple incandescent bulb. Where an incandescent bulb effectively acts like a resistor, right? So when the switch is in the top position, the light bulb is receiving the full amount of power that's being supplied by that AC voltage source. But when the switch is in the bottom position, the bulb is only being supplied with a portion of the AC power that's supplied by the source, okay? So the filament in a light bulb, let me ask you guys something. What do you think the electronics inside of a lamp is? Effectively none, right? Yeah. So for the most part, is a wire and kind of an on-off switch, and then that little receptacle or cup where you screw your light bulb in, right? So is there any, do you think there's any AC to DC conversion going on? Okay. Why doesn't your light bulb flicker? Exactly right. So the 60 hertz frequency that our AC signals in the United States are generated at, or the 50 hertz frequency if you're in Europe, is effectively too fast for the filament of the light bulb to be able to cool down enough for the intensity of the light to drop, right? So light bulbs, incandescent light bulbs, work on a principle called thermionic emission, where effectively if you heat up this material enough, it starts emitting phonons, or photons, I guess, because maybe both, because there's definitely heat involved, as any of you who have ever touched the surface of a light bulb have probably observed, okay? So anyway, the hotter the filament is, the more light is emitted. And although the voltage is constantly changing polarity back and forth, and at some points the voltage is zero, it's never enough, or it's happening so rapidly that the light bulb never has a chance to cool down enough for the light to turn off, okay? So for this diode path here, we're going to see effectively the same thing. We're never going to have enough time for it to cool down, even though there's going to be a small period of time where there's not any voltage that's being supplied, right? So if the half cycle, so let's see, if we have a frequency of 60 seconds, what's our period? Somebody do the math. What's 1 over 60? Should be 16.666 milliseconds, I believe, okay? So out of every 16.666 milliseconds, half of that time, the lamp isn't receiving any power whatsoever. So it's on for 8 1/3 milliseconds, it's off for 8 1/3 milliseconds. It's on for 8 1/3 milliseconds, it's off for 8 1/3 milliseconds, okay? That's still not enough time for the filament to cool down. So what we're gonna see is that our light bulb is gonna operate at a lower temperature because it's absorbing less power. A lower temperature for the filament means that it's emitting less light. So effectively, this is the position for bright, and this is the position for dim, right? So if you have a lamp at home with multiple things, that's exactly what it is. Just one of those paths happens to have a diode so that you can get a dim setting. Unfortunately, that's really one of the only reasonable applications for a half-wave rectifier. You can't use it to power electronics or anything like that, anything complicated that requires a good amount of DC biasing, because of the variation in the output voltage is so large, we can't actually get a good quiescent operating point. So we need to use it for something that responds very slowly. Mr. Martin.
Could you use it in the system, like like filters, like other things to make it useful, or like?
Absolutely. So we're going to talk about how we can filter it to make it useful in literally less than a minute. But I want to talk about two very specific things that we need to take into consideration when we're designing a half-wave rectifier for an application, okay? Those two things are what the forward bias current of the diode is going to be. So we need to know what the maximum diode current will be for our given load. Obviously, if the diode current is expected to draw too much, then it'll fail, right? And it can fail either, it can fail open, meaning that it's always going to be an open circuit and never conducts again, or it can fail closed, which means it's going to look effectively like a short circuit. And so we lose that rectification, or we lose that, partially conducting and partially not conducting response, okay? The other quantity that we need to be interested in is, let me make sure I say this right, the peak inverse voltage, or the PIV, okay? So the peak inverse voltage is effectively the largest amount of reverse bias voltage that is applied, because we also want to make sure that we never get beyond our breakdown voltage, which is going to mess up our rectification as well, right? Because we know that beyond the breakdown voltage, our diodes are capable of carrying large amounts of current. And so we won't cut off those unwanted portions of our signal. So for our simple half wave rectifiers that we have here, our peak inverse voltage is simply going to be the maximum value of V out quantity V out minus V in. And the reason for that is V out minus V in is the reverse bias voltage seen by the diode. That makes sense? So it's the reverse bias voltage because V out is on the negative polarity terminal and V in is on the positive polarity terminal. So what do you think it's going to be? What's the maximum value of that quantity? Look at the graph. V in is the blue, V out is the red. Let me denote something here real quick because I didn't do it. I forgot. This value is V peak minus VD on. So I would argue that our peak inverse voltage here is going to occur at the middle of our negative half cycle, where V out is 0 and V in is exactly V peak. All right. Should be effectively the same for the other one as well. Okay. So that means that we need to choose a diode where the breakdown voltage is greater than or equal to the peak voltage it sees. Otherwise, we're going to wind up pushing it into a breakdown that we don't want. We're going to get negative conduction, right? So in truth, it's much more likely that we'll pick it such that V breakdown is greater than or equal to 1.5 to 3 times V peak, just to make really sure we're never even getting close to pushing it into a breakdown possibility. All right, so our other quantity of interest is the maximum diode current that we are going to see. Anybody have any thoughts on what the maximum diode current or our maximum forward bias current would be in such a system? Obviously, we can't get a number or anything like that, but I feel pretty strongly that we should be able to figure it out.
Slightly greater than,
So I would argue that it wouldn't be slightly greater than that. It would be whenever V out is at its maximum, all of that V out is being applied across our load RL. That's going to be our maximum diode current. Does that make sense?
oh, I thought you were asking what the diode is rated for.
Oh, no. Okay, yeah, so the diode should be rated for slightly greater than that. Absolutely, right. So our peak diode current will occur when our output voltage is at its peak, which is exactly V peak minus VD on. And that divided by R tells us how much current is going to flow through the diode, because it's a simple circuit. So these two things tell us what size diode or what component value diode, not really component value per se, but like a 1N0008 versus a 1N0004 or something like that. It lets us know what to look for on the data sheet to make sure we're not just going to burn it out for its rectification purposes. Okay. So any questions regarding this simple half-wave rectifier? All right. So now let's talk exactly what Mr. Martin was saying. Let's filter this guy so that we can get some use out of it. So we can increase the versatility of our half-wave rectifier simply by putting a capacitor in parallel with our resistor. And I'm only going to bother drawing this version where we're letting the positive half cycles through. This is the in, this is the out, and graphically what this will look like should be something like this. So that's our input voltage, the blue. And our output is going to do something like this, right? So that capacitor, let's talk our way through how this thing works, okay? So when we turn this circuit on, or when we begin the positive half cycle of the first positive half cycle of our input, right? We know that our diode shouldn't turn on or start conducting until Vn is greater than Vd on, which is exactly why we see this little amount of lag, right? And as our input voltage increases, we are going to see that our capacitor begins to charge, and we should see a peak value of the voltage drop across our capacitor of exactly Vn minus Vd on, using our constant voltage drop model, right? Well, once our capacitor has a voltage of Vn minus Vd on, and then our input voltage begins to decrease, what happens to the diode? So if the voltage here at this node is somewhere close to V peak minus Vd on, and this guy is decreasing to less than that, I would argue that diode is now reverse biased, right? So the diode turns off, and then our capacitor starts discharging through our resistor, where that rate of discharge is governed by the time constant, R times C, right? So if we call this time T1 and this time T2, what our output voltage looks like over this particular time is simply V peak minus Vd on, which is the initial value, or pretty close to it for when the diode turns off, multiplied by the exponential of -t divided by RC, right? So this is telling us how it behaves, or excuse me, how it decays until a point where Vn is exactly equal to Vd on again, at which point our capacitor starts to charge again. And then that cycle is going to repeat itself over and over and over again, right? So the rate of decay here is fully dependent on the values that we choose for R and C. We have a very large load resistor. We need a really large capacitor to make this decay very, very slow, right? The goal being is that if the time constant here, RC, is much greater than the frequency of our input AC signal, then we should get what we call a very small ripple voltage. So let me define the ripple voltage here. So the ripple voltage, V ripple, is the magnitude of how much our output decays every cycle before it gets kicked back up when our diode turns on, right? So this guy here is once again V peak. This guy here is V peak minus Vd on. And the minimum value that our output voltage will ever be is exactly V peak minus Vd on minus V ripple, because that's as much as we let it decay ever, okay? So our ripple voltage without any derivation, because it's done pretty well in every textbook I've seen, is simply going to be V peak minus Vd on divided by RC times Fn, which is the frequency of our input signal, right? So we can easily see that the magnitude of our ripple voltage depends on our time constant here, how our system reacts to the change during our transient condition, okay? What do you think our peak inverse voltage will be here? Let me write it up here. It's going to be hard to get an exact value, right? But we can get something fairly approximate. So let's say that our ripple is really small. We have almost a flat line connecting these peaks. What would it look like? What would the difference between V out and V in be? So from this point up here, for that very flat line, down to the axis, we have V peak minus Vd on, and then we have another V peak. So it's just twice V peak minus Vd on. Does that make sense? Our maximum diode current. So let me preface this by saying I'm not going to ask you any questions about this. And let me explain the reason why I'm not going to ask you any questions about this. I have two pretty good electronics textbooks. They derive how to determine ID max in two pretty different ways and get two vastly different results, okay? The equations look extraordinarily similar, but one of them gives values on the order of tens to hundreds of milliamps, which seems reasonable. And the other one, whose derivation actually makes more sense, winds up giving you values of tens to hundreds of amps as what the diode is carrying, which doesn't make a lick of sense practically at all. So I'm going to give you an equation as a placeholder with the full extent that you'll never use it in this class because I don't know whether or not it's true. Okay, so it is an important quantity. I'm unsure how to calculate it until I can derive it myself and figure out which of these two books is making a jackass mistake. Okay. So the value that we're going to say is correct for now is V peak over R multiplied by a factor of 1 plus 2 pi over the square root of twice V peak minus V ripple. Okay. This is the one that gives us the smaller value, but it actually seems, it can potentially seem a little bit weird. And I want to kind of talk us through what's going on here, at least conceptually a little bit, okay? So our diode current ID is going to be a combination of our resistor current IR and our capacitor current IC. Does that make sense? Okay. Well, IR is pretty easy because that's just V out over R. IC is a little bit more difficult though, right? Because that's going to be C times the derivative of the output voltage with respect to time. And so if our output voltage changes abruptly or changes quickly, we're going to see that that contribution of IC is going to force that diode to draw a lot of current for a very small amount of time. Effectively, what the diode is doing is any amount of charge that the capacitor loses, the diode has to quickly inject in this little bit right here. And so that's why we should expect to see a reasonably large forward bias diode current. To me, reasonably large seems like tens to maybe hundreds of milliamps, not tens to hundreds of amps. But again, one of those textbooks is saying it should be that high, and I vehemently disagree, but I like their derivation, so I don't understand where that number's coming. So with no derivation whatsoever and the understanding that this might be incredibly wrong, this is what we're going to consider our peak diode current to be. Okay, I'm a firm believer in using circuit simulations and stuff like that to just see what it, simulate the circuit and then pick one that has a better value instead of mathematically doing anything. Mr. Steen.
So that other one has like tens to hundreds of amps. Is that just like their theory behind it? Is it just super ideal and it's going to be an infinite amount of
Yeah, so it's pushing a whole bunch of charge in over a very, very small amount of time, which means the current needs to be very, very large. It also takes into account the time constant of how the circuit discharges and everything, which doesn't show up here at all, which is why I think that their derivation makes more sense because it takes into account how long it takes for things to charge. But the numbers that you get are just wonky as hell. Because even if it's just for a couple of milliseconds, I firmly believe that if you run a diode at, single digit amps for a small signal dot, maybe a power diode could handle several amps, single digit to tens of amps or whatever. If you run one of those at 500 amps, for 5 milliseconds, I think it's going to burn out. So that's why I'm not sure. like I said, the derivation makes more sense to me, but the values that you get using it seem a little wonky. And I think the reason that the values that you get using it are wonky, so there's the other equation has an extra factor of RC right here. And then effectively it flips V ripple and V peak. V peak is always going to be much larger than V ripple by definition. I mean, the absolute worst case scenario would be they're the exact same things because you're allowing the capacitor to fully discharge. So since V ripple over V peak, it's just weird. I don't know. I can't. I'm happy saying I don't know. All right. The ripple equation I'm good with. The peak inverse voltage I'm good with. The maximum diode current, simulate the circuit, and go from use that base things on. The math behind this, I'm just not sure about. All right, so that's our half wave rectifier with a filtering stage included so that we get a more DC output voltage, right? We're not seeing such a large change. So let's go to the next stage here and talk about full wave rectifiers, okay? And there are two different full wave rectifiers that we are going to discuss. The traditional full wave rectifier, which uses a center tap transformer, and then the bridge rectifier. All right, so our full wave rectifier utilizes a center tap transformer. So here is our voltage VAC as a function of time. Here's our transformer. And there's our center tap. So we're going to have two diodes. One up here, one down here. The output of the diode effectively is going to be pulled together at the same node. And then we're going to have our resistor R here. I'm going to leave some space for when we talk about what happens when we throw a capacitor into the mix. And then this guy jumps over like so. And this is our voltage, the out. Okay, so we have two diodes in our full wave rectifier. So let's talk about why this center tap transformer is critical, okay? So did you guys talk about center tap transformers at all in 224 last quarter? Okay. Center tap transformers are very, very common in households. So that's a center tap transformer is how we take 240 volts, which is what in our homes, things like ovens and probably hot water heaters and things like that, maybe dryers as well use. And then we can step it into two identical 120 volts to go to all of our, like microwaves, lamps, and all that kind of good stuff. So effectively, in our homes, our transformers convert probably something around 13.5 kilovolts down to 240 volts on the secondary, and then the secondary has a tap in the center so that the total voltage drop is at 240, but we get two instances of 120 that are 180 degrees out of phase, okay? So in a similar process, we would see that we'd have Vn of t and negative Vn of t, where the center tap is effectively the common ground for the system. So if we plotted the input-output relationship for this guy, it looks something like this. So I'm going to do in blue, positive Vn, in green will be negative Vn, like so. And then what our output should look like would be something like this. So let's look at what Vn of t is doing, okay? So when Vn gets larger than VD on, then that diode, let's call it D1, turns on. And so we're going to get this portion, and then similarly, that portion of our output, right? So when negative Vn becomes larger than VD on, which is where we're going to get these half cycles here, that's going to turn D2 on. And so we'll have something like this. So where effectively diode 1 is passing the positive half cycles of Vn, and diode 2 is passing the positive half cycles of negative Vn. And when we add those two contributions together, we get full wave rectification, because we see effectively what it's looking like is that the negative half cycle of Vn is being converted to positive. That's not truly what's happening, but that's what it looks like. So we get the rectification for the positive half cycle and the negative half cycle, so that we always have a positive output or zero. Okay. So our transfer function for this guy So let's call this VD on. Let's call this negative VD on. It looks something like this. So it's going to have a slope of +1 over here. It's going to have a slope of -1 over here. And there's going to be 0 when the input is between negative VD on and VD on. So this is V out. And this is V in. Okay. So without a capacitor, what do you think the peak inverse voltage is going to be? So let me label some things here real quick. So this is V peak. This is obviously V peak minus VD on. So this distance between the peak of the output and the minimum of the input is the peak inverse voltage by definition. What is it? It's 2V peak minus VD on. Again, our maximum current just the maximum value of our output voltage divided by our resistor. It's much easier when the capacitor isn't involved. Is V peak minus VD on divided by R. So this is much more useful because we're still delivering. So our half wave rectifier was able to deliver about half of the power of the input signal to a load. This guy is able to deliver most of the power of the input signal to a load. And it's giving everything to be positive. So it's more useful, but increasing the efficacy again involves using a smoothing capacitor, right? So if we put some smoothing capacitor C in parallel, what happens to our output signal? Yeah. Let me do these in purple, right? So we're going to see effectively the same thing. Right? We're going to see that same exponential decay, but now our capacitor, so one way to think about this, we're not allowing our capacitor to discharge for the same amount of time as we were with a half wave rectifier, right? In fact, we're allowing it to discharge exactly half the time we saw previously because we're flipping that negative half cycle over, okay? So it should stand to reason pretty easily that our ripple voltage will be half as large. We use effectively the exact same equation because we're only giving our capacitor half as much time to discharge. Does that make sense? Okay. So with the capacitor, we should see V ripple is exactly 1/2 V peak minus VD on divided by RC times FN. Our peak inverse voltage is effectively going to be the exact same thing. Bless you. 2 V peak minus VD on and our maximum diode current, again, cannot verify whether or not this is correct currently. V peak over R 1 plus the square root of V peak over twice V ripple, according to the textbook that I've chosen to assume is correct. Oh, sorry, thank you. Yes, there should be a 2 pi out front. Thank you very much. Again, never going to ask you to use this, so cannot verify with any degree of certainty whether or not it's correct. But yes, the 2 pi, according to the Sedgwick textbook, the 2 pi should be there. All right, so the principal drawback of this version of the full wave rectifier. What time does this class get out? Okay. Sorry. Well, I'll figure that out later. The principal drawback of this full wave rectifier is that it uses a center tap transformer, which is a reasonably expensive component. Okay. So we can get effectively the same output by utilizing what's called a diode bridge, where a diode bridge just uses a standard non-center tapped transformer. So our bridge rectifier going to look something like this. So here is VAC. And then over on the secondary side, we're just going to have VN. And then I'm going to have a diode bridge. It's called a bridge because it's the same configuration as a Wheatstone bridge. I understand that that means probably next to nothing to most of you guys. But a Wheatstone bridge is an old-timey measurement device used to determine unknown resistor values when you know the others or when they're effectively constant. So let's call this guy D1, D2, D3, D4. Over here, let's put our resistor R. Jump that guy over. And again, I'm going to give myself enough room to put a capacitor in a minute. No weight thing. This is our output voltage. The out of T. Okay. So we double the number of diodes. We wind up getting a very similar output signal, okay? Diodes are cheap, on the order of, nickels or whatever, 25 cents to $1 for really good ones for specific applications, whereas center tap transformers are, tens of bucks and stuff like that. So this is a much cheaper implementation, but it's a little harder to understand exactly what's going on. So let me draw my plot here, and we'll talk our way through the input-output response. So my input signal in blue, as per usual. All right, and we'll talk about what's going on. So let's start with an input signal of 0. What do we think should be happening to literally all of these damn diodes if our input voltage is 0? Yeah, so all of the diodes are off. So there shouldn't be any current flowing through our resistor R. So we shouldn't be generating any voltage drop across our resistor, okay? So as Vn is entering the positive half cycle, what we're going to see is that D2 is going to turn on. So effectively, we should see current is going to flow through D2 because it's turned on. That current is going to flow through R. It's going to cycle back around this way, flow through D3, and then there's the return path for the current up through the transition. So it goes like that. So that's what our current is doing. So the maximum voltage drop that our resistor R should see is V peak minus 2 VD-ons, because there are 2 diodes in the signal path. All right. Now, when Vn starts to get increasingly negative, or when we're in the negative half cycle portion, that is going to make D4 forward biased. Current's going to flow through resistor R. It's going to come around this way. Now D1 will be forward biased. And that's the return path. And so our output voltage is going to look like this. So it's very, very similar to what we got with our center tap full wave rectifier, except that now the maximum value is 1 VD on lower. Donald, do I need to re-explain the signal paths?
I was just wondering if you could erase reverse.
Crap. So when Vn is negative, that means the positive polarity is on bottom effectively now. The negative polarity is on top. So that's why D4 is conducting. The current is going to flow in the same direction through our resistor R. So it's going to give us a voltage of the same polarity. That current is going to flow down through the bottom. It's going to hit this node where D1 and D3 are. D1 is now forward biased. And then our current circles back to the left and flows in a counterclockwise direction through our transformers windings. Mr. Steen.
So does it not go back through like D3 or
So it doesn't go back through. Okay. So it doesn't, so let's look at it. It doesn't go through D3 here because that's, D3 should be negative, a reverse bias. Goes through D4. Should see the other two as reverse. Yeah, and the reason why it doesn't flow through the other two is because it sees them as reverse bias. So if this was an open circuit to begin with, it had to be an open circuit again, right? And it can't flow up that way when it hits this node because this guy is an open circuit. So the same current can't say this is both an open circuit and a short circuit at the same time. Yeah. Took me a second to figure that out. Yeah. So, like I said a moment ago, we get almost the exact same output voltage. What should our peak inverse voltage be? So
2000 both sides for.
Okay. So 2V peak. Okay, so let's think about this real quick, okay? Let's look at the reverse bias voltage across the diode that I'm calling D4. So let me erase this and put our positive half cycle stuff back on here real quick. And all right, so for a positive half cycle, we got this guy, right? Okay. So let's look at this voltage. Let me do it in blue. Plus Sorry, that should be 4. And let's do this voltage right here, which is VD3, okay? So if we're looking at the reverse bias voltage for D4, which is how I've defined these polarities, we could see that VD4 is just V out plus VD3, right? So, sorry, let me erase this. So this is going to be V out minus V in max. So I'm saying VD4 is going to hit its maximum when V out is at its maximum. And then we're going to add to that VD3. Well, VD3 is just going to be VD on because diode 3 is turned on, right? So that's going to look like V peak minus 2 VD on plus a VD on is equal to simply V peak minus 1 VD on. So effectively, you double counted because you didn't take into effect that there were 2 diodes in that path that were both getting reverse biased, right? So the individual diode, D4, we could do the exact same thing for a KVL loop for D1, and we would see that whenever V out is at its maximum, we only see V peak minus 1 VD on, 1 V peak minus 1 VD on. So we get rid of our center tap transformer, and we actually reduce our peak inverse voltage by a factor of about 1/2. So this is a pretty good design. It does double the number of diodes that we need so that we get a little bit more signal loss, but nothing too terrible here. Our ID max in this particular case is just, where the heck did I write it down? V peak minus 2 VD on divided by R. So very, very briefly, let's talk about what happens when we throw a capacitor into the mix, right? Exact same thing as we saw before. We are going to have some exponential decay as our forward bias diodes turn off. We wind up having a ripple voltage. V ripple is 1/2 V peak minus twice VD on divided by RC FN. We have the peak inverse voltage still of just V peak minus VD on. And according to the textbook, maximum diode current of V peak over R, 1 plus 2 pi square root of V peak over twice V ripple. So that value doesn't change. So from an equation standpoint, the only change that we see between our center tapped full wave rectifier and our bridge rectifier is that we get a factor of 2 VD on in our ripple calculation because there are 2 diodes in the signal path for each half cycle. And we get a reduced peak inverse voltage. Other than that, they function practically the same.